Hello, everyone. So first word of warning, I'm not a historian, I'm not an anthropologist, and a lot of stuff I'm going to discuss there touches that. So there might be a few inaccuracies, but whatever I'm talking about, I try to research on various sources, such as the book Calendrical Calculations by Netschum and Berchowitz. It's a great book if you're interested in calendars, and this is a weird thing to say because when I tell someone I like calendars, they're kind of looking at me like I like to take my nail clippings and make statues out of it. But yeah, so there's a few interesting books in there, and the way I like to think about times and calendars is that every time I get started with it, I have this hypothetical scenario of my mind. You look into zombie movies and everything, and there's a downfall of civilization. And I ask myself, how would I survive in there as a computer programmer? And the entire thing is probably I would die within the first week. Sooner or later, let's assume that I'm able to survive for some reason. I developed an interesting set of skills that had nothing to do with Erlang. And I was able to survive for more than a week in the wilderness. I might want to start tracking time. If I'm foraging for canned food, for example, I want to know that it's still good and I won't be dying just by eating it. So you have to start the idea of tracking time, and without a wristwatch, I'm pretty lost. So I thought about it for a while, and the only solution I kind of came up by myself before starting doing the research for that kind of presentation was I'm going to take a stick, put marks on them like the prisoners in movies, and just cross them over. I'm just going to count the days. As it turns out, that's like the most primitive way to count time ever. What we have in the picture there is something called the Ishango bone. And the Ishango bone is something that's 20,000 years old, carved on the bones of the baboon. And really, it's just like a tally system. We're not sure yet if it's something about multiplication tables, a lunar calendar, or just really a counting stick. But basically, me working into the high-tech world of very fancy things put into the wilderness, I have pretty much the acumen of a 20,000-year-old primitive human. Everybody else after that was smarter than me in surviving. So it brings to me the interesting question about how do we do really time accounting. The interesting thing about time is that really there's three big factors in it. You want to be able to count, to predict, and to plan ahead with that. And everything is based on observations. The very, very natural one that every one of us has is really counting days and nights. You go to sleep, you wake up, that's a new day. There's plenty of expressions about that, and you want to look at that way. But even then, thinking about what is a day is kind of tricky. Depending on who you're talking to, a day is going to start at sundown, it's going to start at sunset, it's going to start in the morning, it's going to start at noon or at midnight. In case of ancient China, the day started at 2 a.m. because that's when the roosters were singing, and that's how they decided to start the day. So you might be able to count days with any of these means, and that might be working fine. At some point, you will be seeing large patterns, for example, seasons going through. I'm coming from Quebec, Canada, and we have very clearly defined winters, very mildly defined springs and autumns, and somewhat defined summers. So it's obvious that after a while, you figure out these patterns, you go, okay, there's a thing in there. But you start to think about it, and it's hard to go between just days and years. You want something in the middle, and those tends to be months. How do you base months? Well, if you look at the year, you might just subdivide stuff, or you might be looking at something like the moon, and the moon phase takes on average 29.5 days, and that turns out to be really, really close to the months we have right now, and that might be having an impact. If you're meticulous and you live in a place where it's not that often overcast, you might be looking at the stars, the patterns, how stuff goes. So through history, all these observations dictated how calendars and how time was counted, and that was all related to the important things that these civilizations wanted to track. So if we look into the Egyptians, they have pretty much the first calendar we have on record. And it was an entirely solar calendar, and they had years of 365 days, 12 months of 30 days, and each month was 3 weeks of 10 days. And if you count the days there, you get 360 days in a year. That doesn't match. So at the end of the year, they had like 5 floating days that didn't belong to any month, and those were called intercalary months. So the interesting question is, why did the Egyptians figure out a 365-day year? And the thing is kind of obvious. You just say you look at the sun, you look at how things align, and that's how you get it, right? That's a rough approximation of what we get. But if you look at the Egyptian culture, a very, very important factor in their development, at least until the 80s when they built a giant dam north of Ethiopia, was that there was the flooding of the Nile every year. The Egyptian year was divided into 3 big parts. You had really the flood, the growth, and the harvest. And during the rain season, or just after the harvest, it would be raining in the mountains at the south of the country, and all the water would flow from the mountains, grabbing a bunch of sediments, and then flooding the Nile and yielding really, really rich agriculture. And so it became interesting for that civilization to track this and plan your year around how you can get your crops, how you can sow them, or you can reap them. So that's really how they got to go that way at that point. If we look into more modern calendars, there's the Ethiopian and Coptic calendar that are extremely similar to the Egyptian one, which is no longer being used. The Ethiopian calendar has exactly the same structure as the Egyptian one, just different month names. And they have figured out the idea that you need actually leap years with days to go in between. They, however, picked the same rules as the Julian calendar, which means a leap year every 4 years without exceptions. The Coptic calendar is only used for religious reasons in the Christian Coptic segments of the population in that area. The Ethiopian one is still used as a legal calendar. And this is, again, an interesting thing due to culture. Ethiopia is one of the 2 countries in Africa that has never been colonized, the other one being Liberia. So for Ethiopians, not adopting the Gregorian calendar the way we do is kind of a point of pride into continuing of never being colonized. And for example, the day in Ethiopia starts at 6 a.m., so this is their midnight. You cannot call them with just time zones and everything. It's not enough. They have their own clock system, their own calendar system, and they're going to stick to it. Different calendars you have. The Greeks had a calendar, well, had roughly 12 calendars, depending on which island you were in the antiquity, and they were based on lunar observations. So it's possible that for them, the seasons were not changing nearly as much close to the Mediterranean, or maybe they really cared a lot about the factors such as a full moon giving you good visibility at night, a new moon giving you nothing, or they were extremely aware of the tides, and the tides have to do with the level of the moon in the sky, because when the moon and the earth and the sun are aligned, the tides are much higher, and that tends to fit around the equinoxes and solstices. So maybe that's what they had, but roughly what they had was a purely observational calendar. They would go out at night, look at the moon, either it's a new moon, maybe it's a full moon, maybe it's the first time they see a crescent moon in that period of time, and they decide that this is a new month. And that gives them 12 months based on 12 moon cycles, and every one of them averaged 29.5 days, which gives you roughly 254 days in a year. So that's kind of okay. It's close enough to a solar year. If your seasons drift, it's maybe not too bad in Greece. It's no longer being used, but the Islamic calendar used in multiple Muslim countries right now today is still a legal one. It's still fully observational. And really the way they work is that many Muslim countries have a religious authority that go out at night because their day starts at sundown and look at the moon cycle. And if they spot a new moon, this is a new month. If the sky is overcast or if they cannot see it at the right time of the day, well, sorry, the new month is going to start tomorrow. So you can have something like 15 different countries based on the same calendar, but every one of them has different dates because the observation time was different. And this is still how it works today. So that kind of works, but much like the Greek calendars, there is a mismatch between the length of a solar year and the length of a lunar year. And the 11 days that you have, or roughly 11 days, gives you that every 32 solar years, there's 33 lunar Islamic years that are being spent. That caused interesting problems in the past. Around the 15th century, the Ottoman Empire was already using that calendar, with the caveat that all the expenditures of the government were being paid according to the Islamic calendar and the lunar cycle, so paying the army and the military and stuff like that. But the taxation was based on agriculture and fisheries, which is seasonal and affected by the sun cycle. So what would happen at that point is that every 33 years of expenditures, there was only 32 years of revenue. And they would be having what is called a skip year, where they would keep expending stuff but getting no money to pay for it. So in 1852, in the Islamic calendar, which is 1448 in our calendar, there was an invasion force coming from the Serbians and the Hungarians. And while they were being attacked, storybooks mentioned the fact that due to the skip year cycle that they were having, the military salary was 6 months late, and that really played a big role into them being demotivated and yielding a successful invasion of part of the Ottoman Empire. So this is not to say that the calendar is a bad one, but it's to say that the calendar you're using or the method you use to account for time should really match the actual needs you have. If your expenditures are matching on one calendar that doesn't match how you bring the money in, you're going to have trouble, and that's what they had. So not wanting to be undone, the Babylonians had their own system. The Babylonians in Mesopotamia seem to have invented everything, right? First writing system, they have fancy calendars, the first battery like 1,000 years before anyone. So they have a fancy calendar. It's both lunar and solar. So it is still moon-based. They still have a concept of having 12 lunar months, and it started as an observational one where people would get out and really look at the crescent moon. And then if they saw a crescent moon, that was a brand new month. So the thing they did, though, unlike the Greeks and the Islamic calendar, is that they also tracked the solar year at the same time. And they did notice that drift. And they noticed that once every 19 years, the cycle would complete and there would be a full gap year, a year that would be skipping whatever in the way they were doing it. And so they decided that if we decide by decree to just inject months here and there into our cycle, we can keep the seasons and the moons in sync. And this is what they did. But to fix that system is that starting something like 499 BC, they started making all the calculations to make it work, and they wanted to stop having an observational calendar where they needed to get out and look at the sky and have something they can count. And to fix that and make it work took them over 100 years. Eventually they did it, but that gives us like the 3 basic types of calendars. It's just that to develop a system that is this fancy, such as counting 2 things at a time, it takes you something like 100 years. It's on par with the software we develop, I think. Icelandic calendar is kind of a fun one. It's one of the rare calendars that has been developed outside of early civilizations and outside of close to the equator. So for them, the concept of the day still exists, but is far less reliable. For example, if I'm trying to celebrate Ramadan in northern, in Iceland directly, it's pretty difficult because if you don't have the right to eat until sundown and you have a midnight sun, you're kind of in trouble. So they have this concept where the year is divided into 2 seasons. The summer has 180 days, and then the winter kind of matches in between the rest. Roughly 180 days, a bit more to fit a full year. And what they do is that these 2 seasons are divided into months, but the months don't bear a lot of significance. What they care about is the number of weeks. And every 6 or 7 years, they insert a leap week into the calendar to move forward. In modern day times, it's no longer being used except for holidays. And the thing that they do with it, the only modern calendar that uses weeks like that is the International Standard Organization calendar for businesses, which uses week numbers to plan ahead for budgets and everything. So we have that stuff, our basic calendars. So I want to look at a few specific calendars right now. We have the Hebrew calendar, and I say that this one is coming to backwards compatibility because in terms of legal calendars that are still in use in the world, it's pretty much the oldest one. It's multiple millennia old. It's been patched multiple times to match for stuff, but it's still roughly the same one that's been used. So they are extremely inspired by the Babylonian calendar. They have that concept of 12 months or 29 or 30 days based on the moon cycle. They have the principle of leap months, the same way the Babylonians have them. And the only interesting difference is that while their days have 24 hours, each day is also divided in 1,080 parts of 3.5 seconds each. And this is a remainder, again, of the Babylonian origins. So up to that point, it kind of makes sense. It's a bit unfamiliar with people who don't know that system of calendar, but it makes sense. The problem is that the Hebrew calendar is full of business rules. And I want to compare that with software. The way they have is that they have concepts of holy numbers, unholy numbers. They do the same thing with days of the weeks, what is acceptable or not. So to pick the beginning of the new year, it sounds kind of simple. You're just thinking when the calendar is over, the next day after is the new day of the year. That doesn't work in the Hebrew calendar because you have these rules about which days are allowed to be legal or not. And this is how it works as a legal calendar in Israel today. So there's like 4 rules about that, about how to pick a leap year and how to delay the new year. The first rule is kind of simple. If the time of the mean conjunction of the moon is at midday or after, then the new year is delayed. That's okay, easy to understand. Second rule, in no event may the new year be on Sunday, Wednesday, or Friday, otherwise this rule combines with the previous rule and results in a 2-day delay. That's kind of okay. We see the kind of software spirit into that thing. Now the problem is that you run that and after a while you find a new bug, and that gives you rule number 3. In some cases, about once in every 30 years, if Rosh Hashanah, which is the new year in Hebrew, were before noon on Tuesday of a common year and the conjunction of the following year at midday or later, then applying the previous 2 rules will require an acceptable year length of 354 days, and thus the current Rosh Hashanah is delayed until Thursday. All right, we patched the system. Ship it. Rule number 4. In rare cases, about 1 in every 186 year, Rosh Hashanah is in Monday after a leap year calendar posed similar problems by causing the year to be too short. But the prior New Year conjunction was on midday on Tuesday and was therefore delayed until Thursday. The conjunction went from midday to Tuesday of the previous year, and then the current year would be after 9:32:43 and a third a.m. on Monday. In this case, Rosh Hashanah is postponed from Monday to Tuesday, extending the leap year just ending from 382 to 383 days. The current year cannot become too short because of this delay. It is shortened from 355 days to 354, with the following Rosh Hashanah being delayed until Saturday. Easy! Who wouldn't do it? And I shortened the text there because it's 2 entire pages in the book. So yeah, it's backwards compatible, but much like software, you patch it and you patch it and you work for that. And eventually you find out that it still works. Everyone is really happy they don't have to change calendars, but there's only like 2 people in the world who can maintain it. Different approach is the one that we have in the calendars we know, the Gregorian calendar, which has history in the Julian one and history in the Roman calendar. So the historical Roman calendar was based on the Greek calendars. They were lunar, they were observational, but they didn't really like base 12, they liked base 10, right? So they had 10 months of 30 or 31 days, and that gives you roughly 304 days in a year. And then from January to March, I guess they got kind of lazy about counting about that, and you just had a bunch of days in there. Eventually, the king of Rome, called Numa, represented his people and decided that even numbers were not a lucky thing. And so he took all the months that had 30 days, made them have 29 days. That created 57 days that were slack. Created January that has 29 days, and then February 28 days, which has an unlucky month, and that was how it went. So that was okay. That was the Roman calendar, 12 months, these kinds of days, and everything. In 46 BC, Julius Caesar comes in. It's like, this is a stupid calendar. I hate the moon. Let's align with the sun. And so the alignment was done, and they decided and had observed that the year was not 365 days, but 365.25. In truth, it's a bit less than that, but I guess the Romans were kind of going, yeah, it's good enough. So they had the leap year every 4 years on a calendar of otherwise 365 days. So what happened is that, of course, you just think, I guess, it's not going to be used for like 1,000 years, maybe 30 years. I can't believe they don't make a new calendar until then. And no, it gets to be used all the time like software. So in 1582, the people are doing their calculations like, there's kind of like 10, 11 days missing in the calendar, and they figure out that the time was not good. So Pope Gregory in 1582 decided that, you know what, we're making a new calendar, we're changing the name, we're breaking backwards compatibility, this is the Gregorian calendar. And so the only thing they did is fix 0.002% of the error by saying that all the century years not divisible by 400 would not be leap years. And so that happens that 1900 is not a leap year, 2000 turned out to be one. And that fixes it. The problem is that for that little fix of 1 day out of every 128 years, it took a long while to adopt. So in 1582, that calendar was adopted. And all the Eastern Orthodox churches in the world took a while to agree with that. And it wasn't until 1924 that all the Orthodox countries had actually made the switch. It took them over 300 years to do it. So you look at that and say, yeah, that's kind of hard. Some of the countries actually didn't even want to switch. They just reviewed the Julian calendar and ported patches back so that until the 2800s, it aligns with the Gregorian one. And then the people in the Julian calendar kind of got into this kind of infighting about which Julian calendar is a true one. And so they all switched to Gregorian except for religious holidays. So that's kind of interesting. But again, like software, this is a painful transition. And the most painful aspect of it, and I like that one very much, is how Sweden has done the transition. And Sweden, knowing about Erlang and OTP, wanted to do something that was extremely easy to switch over with a well-planned deprecation plan. So in 1700, they decided that they needed to roll back 11 days to match the Gregorian calendar. And they decided, you know what, for 40 years, we're not going to account for leap years, and then we're just going to have rolled back progressively. And so by 1711, there had been 2 leap years, and they said, you know what, this is a stupid plan. And so they cancel it, and they roll it back, and in February 1711, there's a month of February in the Swedish calendars that has 30 days. And so they kind of went, that's all right, we're just going to stick on that version, it's good enough, what could happen? In 1753, they decide to switch, but knowing that a slow and easy transition is kind of difficult, they said, screw this, we're going to go with an actual direct transition. So the month of February in 1753 only had 17 days in the Swedish calendar. It's a fun one. So if you get dates from there, it's just kind of like, yeah, February 17, March 1st, there you go. So I think this, aligns funnily with software. I think it's kind of the same, but we see it as a century scale in that case. So I want to look into last calendar before getting into the fancier stuff about modern times and computers. And I want to look into the Chinese calendar. And what's interesting about Chinese calendar, and it's the same with the Hindu calendar, is that instead of being purely observational or purely arithmetic, where you do the calculations about how long a year is, those are based on astronomical facts. So at the core of that is the concept of the ecliptic. And if you don't know what it is that if you look at the horizon, at a given time in the day, every day like that, the stars, for example, behind which the sun aligns, changes. And so if you look at your zodiac signs in newspaper, which I'm sure everyone here does, you will see something like the sun enters into Aries or something like that. So this is the alignment of where the sun is. And it turns out this is extremely in lockstep with the solar cycle of the Earth going around the world. So the thing they do is that you take that ribbon and you spread it into a 360 degrees kind of rectangle that represents your sky, and you're able to trace the progression of the sun over there extremely accurately. The other thing that the Chinese calendar does at that point, in one of their 50 editions, because they have many of them in multiple revisions, some of them that were used at the same time in different environments, was use the moon to count months still. The Chinese calendar is a lunisolar calendar. And they therefore use cycles or 12 or 13 months because that's what fits the best with a solar year. And this is how the Chinese year is defined. And that's why it's kind of confusing every year for us to decide. This year is on February 8th, but it has to do with the moon cycles. So the question here is, how can you automate that principle of having leap months in lockstep with the solar year and the lunar calendar, just by looking at the stars and saying, okay, that's how we do it, it's going to do itself on its own. And in the past, the Chinese calendar was being done by like the royal departments of mathematics that would make one big calendar and then show it to the emperor. The emperor said, yeah, that's good, I like the colors. Can you make the logo bigger? And then they signed it into an edict. And then they made copies of that calendar and they brought it to all the different regions of China where they could be reproduced after, I'm sure, paying copyrights as required. So, yeah, they use that kind of system of calendar. And the thing that they do is that, yes, they have the lunar months based on the new moon, but for the solar year, they did take that sky, the ecliptic, and divided it in 24 equal parts of 15 degrees. And for each of them, they decided that some parts were major and some parts were minor. So degrees 0, 30, 60, 90, 180, and whatnot are major. And they turn out to align with like the solstices and the equinoxes. And then the other ones, degrees 15, 45, and so on, those are minor. So the way that the thing goes is that you look at the moon, and when there's a new moon, you know you're entering a new month. But you compare where the sun is through the ecliptic at that point, and that gives you, for example, the name of the month that you're going to have. So how do you do the leap structure? They decided that the 11th month of the year will always start during the month of the winter solstice, which will always be a major term. So by the pigeonhole principle, as you go there, you just count the new moons between each of the cycles, and that's how they get through it. So, oops, that's not what I wanted to do. So that's how they get to it. And by having how many moons happen in there, you're bound sooner or later to have 13 moon cycles between two equinoxes rather than having only 12. And that gives you a leap month. And to pick which month in the year is going to be the leap one, they look at whenever the solar term is twice a minor one, a single month, and they go that month is longer. So it's automated. You just have to calculate the sky, and it's all taken care of. The interesting bit about that is that this calendar is somewhat still legal in there, even though they use the Gregorian calendar. And it's the same with the Hebrew calendar in Israel. They use the Gregorian calendar, but the Hebrew one is also valid. And what's cool is that this gives you this kind of offset between them, where you can have your birthday counted in both calendars, but because of the leap structure, it's possible that in one system, you're a year older than the other one with a month difference. So when you get, for example, in Israel, and you might be old enough to drink or drive in one calendar but not the other, and you get a parking ticket or you just get a driving ticket, you can go to the court and say, according to this calendar, I'm old enough, and then they have to wave you through. It's an interesting thing. It's interesting because it's happening right now in parts of China. It's happening still in Israel, but there's nothing that tells us it won't happen in the future in a place where we actually have software running. For example, any place that could be running the Islamic calendar could decide to have the switch, and then you start having to support both calendars at once. Another thing about the calendar is that they used to be counting the years in terms of this is like the third year. This is the third year of the fourth emperor of the whatever dynasty. In 1912, there was a revolution, and politics being what they are, they decided to reset the calendar and basically stop counting them in dynasties. They put the epoch, the starting point, in 2698 BC in some of them, and if you look at the Taiwanese one, they actually put the epoch as January 1st, 1912, or their equivalent of that. So at that point, if you look at Chinese documents, historically or not, there's two possible manners to account for them, and you might have to compare them. It's tricky. And other stuff gets more tricky. Mayan calendar uses day counting, multiple nested cycles, counts for 100,000 of the year. Persian calendar is like the Ethiopic one, except they use astronomical events. Baha'i calendar is for the Baha'i faith. They count cycles of 19 years, of 19 months, of 19 days each. And they have a leap structure in there. French Revolutionary calendar lasted for less than 20 years. And they had like a concept of 12 months or 30 days with 5 or 6 trailing days and 3 weeks of 10 days per month. So you have all these extremely complex calendars that took millennia to get going and to get fixed properly. And then computers people are like, seconds from January 1st, 1970 is going to be good enough. So what's interesting is that the computer people of the 70s were very, very smart engineers, but they did the same thing I do in my hypothetical survival instinct. I just go in counting notches. And you go back 20,000 years in the past, and this is computers now. And I mean, it makes sense because the only thing a computer can look, it cannot look at the moon, especially the size they had. They can just look at their clock cycles and increment them. But what could go wrong? Everyone remembers the bug of the year 2000. We learned from that, so we're going to have another one in 2038. That was super cool. That's when the integer for the epoch rolls over. 2036, NTP clocks reset. 2042, IBM mainframes, which I'm sure I'm not going to be used anymore at that point, are also going to reset. Microsoft Excel was replicating a bug from Lotus 123 that assumed that in the year 1900 was a leap year. That wasn't true, but decided backwards compatibility is great, let's pretend it was, and then that made it to open standards. There was a shuttle launch in 2006, 2007. I don't remember the exact name of the shuttle. And they were having the launch planned something like the first week of December, but due to some delays either in production and weather, they might have had to delay it until the third week of December. If that were to happen, they decided, you know what, screw this. We know the computer on that shuttle, and we know that once it goes through 366 days, it keeps going up. And rather than having the entire flight go with that calendar that doesn't reset, they don't know what happens, they just said, you know what, if that happens, we wait until next year, that's when we launch. If you set your date to January 1st, 1970, you could brick your iPhone like a few weeks ago. And if you were presenting to be an Apple time server on the local area network, you could brick the phones of everyone. That was great. We've all seen leap seconds with the JVMs locking up due to the Linux kernel and laughed at that because Erlang was not impacted. As I said, Taiwan uses a calendar similar to the Chinese one, also reset at that point, so they had the year 100 bug a few years ago. Google Calendar has super fun meetings. There was a bug at a point where if you were before the daylight saving changes time, and you set a meeting after that, it would set the meeting to the time at where you were when you set it. So if I had friends for breakfast at 9 a.m., they would actually show up at 8 a.m. because notification was wrong. There's no clear good way to do that. And there's a few more of them. So aside from using good calendar library, what can we do? This is your brain on timestamps. Timestamps can work reasonably well on a single machine. You look at the thing, you pick UTC because you don't want to deal with time zone. It's UTC, it is. And you just really pinpoint an event in time. So single computer should be fine, so I decided to run a little experiment myself. I took 4 systems, my phone, which remained in sync with my carrier, this laptop, which I disconnected from the time servers from Apple, and then I took my microwave oven and my kitchen oven, and I synchronized their clock to the same time. After roughly 3 weeks, 3 weeks and a half, when I was writing that slide, I compared their timestamps. And so the microwave oven was like drifting 3 minutes in 3 weeks. The laptop turned out to have drifted 2 minutes and 16 seconds in that time, and my electric oven, that bastion of hi-fi clocks, was actually up to date and at the right time. So the interesting thing is that the clock tolerance of my laptop is equivalent to one, or maybe worse than one, of a $15 wristwatch. So it's interesting because what happens in there is that we cannot really trust the internal clock cycle of our computers over a long period of time. Voltage, heat, all impact the frequency at which the crystals, or whatever it is, how they work, function. It impacts how it goes. So to deal with this, people came up with NTP, and NTP is a bunch of atomic clocks that interrupt an OS at every few nanoseconds to update the timestamps, and then you synchronize layers and layers of servers with fancy algorithms to go with that. And if you look at NTP algorithms on Wikipedia, you know how math pages are. The math pages are like full of proofs and everything. It's hard to understand. You go into the NTP page and they're like, it's a lot of very complex calculations. It has to be tough because even Wikipedia doesn't expand on that. So yeah, what NTP does is that it corrects time. And if we know that it corrects time, we admit by definition of using it that it can roll back the clocks on your system. So timestamps can maybe work, maybe not. You get that kind of stuff, and this is how the Erlang VM does it. This is actually a talk that mentions Erlang at some point. You have the OS system time. This is about how you count time as a human being, the point in time. I have an event, and I want to pinpoint it at some moment that people can refer to. That works fairly well for timestamps. It has a limited resolution. And then if you want to do something, I want to compare one event after the other, visibly a timestamp doesn't work because it can be rolled back. So what you want to start having is a monotonic counter that never decrements. And so you're able to always have them go that way. That works fine on a single system. And if you want to count the differences between two events to see how long it took before the beginning and the end of something, that's what you do. Now the problem you get in is that in distributed systems, these monotonic clocks are not being synchronized, and so you get the same problem of clock drift that you have otherwise. And so that brings a super quote of Les Lamport. In a distributed system, it is important to realize that the order in which the events occur is only a partial ordering. There is no way to provoke an absolute ordering just by looking at clocks. You need a protocol that will serialize everything, but otherwise, the events are only giving you a partial ordering. And so Leslie Lamport, who on his own has been inventing the distributed systems kind of stuff, came out with Lamport clocks. And what Lamport clocks do is that they looked at things and they said, well, you know, the semantics of times and everything, we can kind of replicate these. And so every process that we have in our system is going to be having an internal clock that is going to be logical, not impacted by time. And it's going to be set to 0. So every time, for example, A writes something here, sets the value of the clock to 1, sends a message to B, B receives it, increments the value, and then you track that logical progression. And so when you arrive here at that point where you get to C, C increments the clock, and you know that if you look at the timestamp, C has newer information about the state of the system than A did, because they have different clocks. So when C modifies the value, increments it to 4, sends it back to A puts it to 5. B here is not aware of that change. And so the interesting thing is that if B modifies its own record and sends it to C, C looks at the time and says, that is older than what I had, 5 wins, 5 is the pro there. And so you just lost a write. And that might be problematic, but it might not be. So if you're using timestamps usually and just looking at time, this is the same kind of semantics. You don't really care about the causality of the events, you just care about having a partial ordering, and that respects that. So there's an entire thing called hybrid logical clocks, which were created out of frustration because Google have fancy GPS clocks, and they kind of pissed everyone off when they published a paper on Spanner. They were like, well, we have these clocks, they're super accurate, we don't care about eventual consistency anymore, up yours. And everyone was like, well, okay, we're going to do our own poor version of that. And they did it with hybrid logical clocks. So the way they do it is that you look at NTP and stuff like that, and you know that between a few milliseconds or a given interval of confidence, your clocks are going to be synchronized. And by looking at the synchronization, you know that if the two events happen at a distance higher than the part of uncertainty that you have, the timestamp can be trusted for the order of the events you have according to the semantics you required. What happens, though, is that when the two events get to be really, really tight in that spot where the clocks are really close together, you lose that aspect. So the thing that they do is that they just plug a Lamport clock on top of that, and then you get that ordering to be respected, even though the time synchronization is not trustable. And so if what you want is these kinds of semantics that I want really good timestamps, and I like the semantic of timestamps, even if maybe you shouldn't, you are able to replicate them even though you have computers that roll back and forth in times. through that mechanism. Then you get people with vector clocks who are like, you know what, I don't actually care about having accurate time in that stuff. What I really care about is detecting that conflict that we missed with the Lamport clock and that we would have missed with any other timestamp mechanism that were not based on logical timestamp like that. So the Lamport clock starts with the idea that instead of having, the Lamport clock starts with the idea that there's a single counter for the entire thing. The vector clocks can be seen as just a tiny improvement on that, where you track one clock per process in your system. So in that case, A modifies it, and so the counter for A is bumped by 1, but the one for B and C are still left at 0. When you send the event to B, B increments its own versions, leaves the one from A there. And so in that counter, I know that A has seen the current state, I know that B has seen the current state, I know that C has not seen it. And you track it that way, and you increment them slowly. So as you look at the events here, for example, 1, 1, 2 is being sent to that one. The way we compare them to know there has been no conflict is I take each element and I compare them to each other. So the element 1 here is equal to the element 1. There is no conflict. Nothing has changed as far as I can say. Then I look at B, and the element 1 here is bigger than the 0 I had, so it's a newer clock. And I look at C, and it's bigger than what I had. So I take the clock, I merge it with mine, and I increment my own version to say I have seen this, and I say that it is OK. When I get to the conflict, I do the same comparison. But what happens is that in some cases, I cannot say the same. So I check the B timestamp, which is 1, 2, 0, and I check the one I had, which is 1, 1, 2. 1 and 1 compare equal. This is OK. 2 and 1 compare bigger. So technically, the B clock should be bigger. When I get to the other point, I say, oh, C is bigger than B. Then I detect that the two updates have not been seen by anyone. There has been no coordination at that point. And I detect that the causality of the two events cannot be reconciled. There is a conflict in the system, and I know about it. So the way to solve it is either to pick a winner or to track both conflicting entries. And when someone reads them, it can say, well, this is what I want to be the canonical version. And when you do that, you increment the clock for one that is bigger than all of them. And then in the future, when any of the other systems look at it, the newer version that is now conflict-free takes over the other ones. And that's how you do your tracking at that point. So that was kind of nifty. The problem you have with vector clocks is that you have to be really careful about how you grow them and about how you shrink them. Because the nodes in your system all have to track their clock, and you have to keep track of them as long as possible. And if you are adding nodes in the wrong order, you confuse the tracks, or you reuse a thing that's not valid, you can break up the causality tracking. And if on the other side you remove clocks that you shouldn't have removed, you get into trouble. So doing all of that is extremely complex with vector clocks, and there's companies, I don't know if you've heard of the word Basho, that kind of deal with that problem. There's kind of evolution. It's extremely similar. Those are the interval tree clocks. I'm not aware of a system that uses it outside of toy database I write in my free time. But it's really, really a cool paper. And if you can just look interval tree clocks paper, you will see diagrams like that. It's one of the best styles of papers I have seen. And the way to do it is that they still maintain that kind of mechanism of incrementing counters. But instead of having one for each of the nodes, they take that ID space, the gray rectangle, and they divide it and fork it between nodes. So I only need one node in the system to give me the part. So when I fork it right here, I have the left half and the right half. And so when I increment the left half, I just increment over my ID. I just increment over my ID. I fork again, and now I have the left quarter, the second quarter, and the other one is independent. So this is how I split my IDs, and this is how I join them together. I no longer need to have a fancy mechanism of quorums to get everything to agree to this is now the cluster shape. You can just kind of put nodes in and out of it, and that's super cool. And when we look at the same diagram, it's a visual version of a vector clock, roughly, and it has the same stuff. I increment my ID based on that one. I increment it, so now I have the 3/4 on there, and then I increment that one. We know that the clock is all equal. This is equivalent to 1, 1, 1. This is equivalent to 1, 1, 2. Then I send it there. This is equivalent to 2, 1, 2. And I can do it that way. And when I detect conflicts, I just compare the shapes like that. The algorithm converts the shapes into actual tuples, if you look at the Erlang implementation. And you can compress and go them up that way. And so they're a super cool way to get that kind of fancy mechanism. And at some point, there's, multiple other ways to do that kind of things. There's iterations like dotted version vectors, dotted vector clocks that find conflicts in different ways. But like the basic type zoo is really looking like these things and then improvements over that. And then you think about all that stuff. You say, this is freaking terrible. I hate it. And you decide, screw time, I'm not doing time anymore. And you get into CRDTs. And CRDTs is just like, you know what? If I just think of all my operations in ways that can never conflict, either by making them convergent, which means I send a bunch of people in the room, please find me the tallest person you can find. No matter in which order they report it to me, I take the tallest person, and that's the final answer. The order doesn't matter to get my answer. There is not going to be any conflict. And the other one is to take commutative data types. So I can take 5 people in there, tell them, go pick up the pockets of everyone in the room, I want their money. And no matter in which order they pick the pockets, I get all the money anyway. So the answer is always right. So what you do with CRDTs is you start with that basic operation that's commutative, like the addition. You can build a counter that increments forever. And then you look at the counter and say, yeah, that's cool. How do I subtract that? Subtraction is not necessarily commutative if you do it that way, and you cannot always reapply it. So you make a counter for positive numbers, and then you make a counter for negative numbers, and then you just add to them infinitely because that works. And when you read it, you just make the final application once at read time every time. And then bam, you solve the problem. You now have a counter that can increment and decrement and do it for free. Never need to synchronize except to get the newer values, but you don't need to be right. And if you use these counters and you look at number theory and that kind of stuff, you're able to encode everything with numbers. So sooner or later, you take that and you expand it, you're able to build stuff like sets, arrays, maps, graphs, and all kinds of really, really, really fancy types. And the job of researchers is really about making them fast, I guess, rather than anything else, because, yeah, you can expand on these, and the concept gets there. So they are super interesting because you don't want to deal with time. I guess the big challenge that you have with them is that you cannot represent everything with a CRDT. You're stuck with the limitations of the data structure. So if I have a bookstore or I'm trying to sell a book, I can do with a CRDT very well the operation, tell me how many books I have sold in multiple shops without synchronizing. What I cannot do is, say, for example, sell almost 50 books in all these stores, because this requires an ordered agreement about how many books have been sold at some point, and CRDTs don't want to worry about that. That implies that time is involved, and you don't want time to be a thing. So this is kind of big infernal machine, I think, about time. And we go from that system that took millennia to develop, and they're always based on observations. And what's interesting about observations is that they are triggered by things that we feel are important to our culture, to our location. They're extremely localized. And so when we start dealing with the stuff like the Egyptians, they really cared about flooding of the Nile. And when you start looking at different stuff like the Julian calendar, or rather the Roman one, they were just really hating even numbers. And that had an impact in the structure they had. So when we work with time on computers, I think the really, really dangerous thing to do is to just use a timestamp because it's easy. If we want to pick a good mechanism to deal with time, we have to look at the needs we have and what we want to measure. If you're trying to learn about history and you care about the fact that this is a centennial of World War I, you know that there's going to be an event at a specific date that New Zealandic and Australian peoples are going to care about. This is the Battle of Gallipoli in Turkey. At the point, it was the Ottoman Empire. But if you're trying to understand how the war went, it is much easier to see it as a sequence of events that happen. And the same is true with how you try to understand the stuff that happens in a computer. If you just put timestamps in there, you get this kind of thing that is about this absolute value. If what you're trying to do is understand a sequence of events, you might want to start thinking about how to count time differently and start thinking about logical time and these kind of things. And the stuff you do and the stuff you care about really has an impact about how you should implement the solution. And we should take care about that to avoid the cases, for example, of the Islamic calendar that led to an invasion because the stuff didn't match what you actually wanted to do with it. So I think this is a tiny distinction, but you have calendars that have been used for thousands and thousands of years, and we have software systems that have been used for like 60 of them, and we hate them. There's maybe something, I guess, we should learn from that kind of time representation. And aside from picking the right representation, I think the big lesson is please be very scared of dealing with time. Any questions? Yes, Kenji?
You haven't mentioned about the Einstein's relativity theory about time. Time is the place.
Right, yeah.
Dependent on the place and the velocity.
Yes, that is a good point. I skipped on that. Kenji mentions that due to Einstein's relativity, the time depends on the place and on the location you are, and this is entirely true. And this is true even if you look at calendars without relativity. If you look at the Chinese calendar, all the measurements are taken relative to Beijing. If you look at the ones in India, they're taking relative to Ujjain. And if you look at different things, the place you have has an impact through cultural reason, but it does have an impact also through locations. And if you look at GPS clock, they have to account for the fact that because they're going faster in space than we are by our frame of reference, the time in the satellites for the GPS system goes at a different pace than the one that we do on Earth. And I'm really, really afraid that at some point people are going to make people immortal, and in 2000 years I have to deal with a calendar system that has to deal with gravitational clock drift in interspace travel with software. I dread that day. I'll probably just choose to die instead of live infinitely. Any other questions? All right, I think that's it then. I'll be around if you want to ask them in private. All right, thank you.